Okay, so we can start. It's a couple minutes early, but let's get started. Just let me start with some announcements. We have put out lab number 3. Okay, it's due in early May. I think May 3rd is when it's due. The lab has a extra credit part in it, which is completely optional. Okay, some of you have asked whether there is any extra credit work you can do. You want to make up for any points in some other assignment or exam. So we handed out an extra credit part. Don't attempt it until your lab 3 is in good shape, because you don't want to lose points in the main lab trying to do the extra credit. If you finish the lab and have time, you can, of course, look at it. The extra credit part actually is based on paxos, which is what we are going to cover today. So as of today, most of what you need to know would have been covered in the lecture, so you should be able to complete the lab. Okay. As an aside, we will hand out another lablet this week, which is going to be on cloud computing. Okay. The third lab asks you to deploy your code on the cloud, and we'll give you free accounts on the cloud, so you don't have to pay for it. Okay. So the lablet will actually tell you how to activate your account. You may have gotten some email from AWS already, but we didn't tell you what to do with it. Okay, the lablet will tell you how to activate your account, and then you can use that for your lab. Okay, so keep an eye out for the lablet, which will come out, I think, in a couple of days' time. Right? Okay, so let's get started. Today we will continue the discussion from last time when we started talking about distributed commit. I mentioned that distributed commit is a technique that allows you to give you all or nothing properties to some operation. Okay, we have looked at transactions where we had this all or nothing property for a set of instruction. Distributed commit is going to generalize that for us, and we will essentially complete the discussion on distributed commit that I couldn't do so last time, and then we will continue the discussion, talk about consensus and 2 techniques for consensus, which are paxos and RAFT. Okay, so let's start. So here is where we left off last time. So I presented this 2-phase commit, also called 2PC, as a technique for implementing distributed commit. Now, as an aside, do not confuse 2-phase commit with 2-phase locking. They sound similar. This one is called 2PC. That's called 2PL. Okay, they are completely different things. One is talking about how do you get locks in the context of transactions. This one is just talking about how can you get all the nodes to decide whether to abort or commit a transaction or any operation. Right? Doesn't have to be a transaction in this case. Okay, so there are 2 different concepts, so don't get them confused. But having said that, how does 2-phase commit work? So it has a coordinator, and the coordinator is just going to ask all of the participants whether to commit the transaction. I keep saying transaction, operation. Okay, commit the operation, which means it successfully completes, or abort the operation, which means you have to undo that operation. Okay? So all of the participants will get to vote. Okay? If everyone votes commit, then the decision is to commit the operation. Even if one node says abort, okay, then you abort the operation. So this is not a majority vote. Okay, an abort is essentially a veto. So which means that if one node says no, something went wrong, we need to undo everything, all the nodes have to undo it. Okay, so that's the basic idea. So you will see this is described using a state transition diagram. The first one is the coordinator. The second one is all the participants. So initially, you're in the init state, which means you're starting, and then you send a vote request, which means you send a request to all of the participants saying, should you vote for what you want to do? And then the coordinator goes to wait state, waiting for the votes to come in. The votes come in, it looks at all the votes, and if all the participants have said commit, then it basically sends a global commit to all of the participants saying, go ahead and commit the operation. If anyone has voted to abort, you send a global abort asking all the participants to abort the operation. Okay? This is the coordinator. Okay? Here is how you can view each of the participants who are also voting. Okay, so initially all the participants are in init state. Okay, so if when you get the vote request from the coordinator, if this participant decides to abort the transaction, it's going to send an abort to the coordinator and directly go to the abort state, because this coordinator does not need to hear the results of the voting, because if this participant knows that if it votes to abort, then everyone has to abort, so it can directly make the transition. Otherwise, it sends a commit request to the coordinator and it goes into this ready state where it's waiting to hear back. Okay, because the coordinator now has to collect all the votes, and if the coordinator sends a global abort, then you make a transition to abort. You abort locally. If it's you get a commit vote, then you commit the operation locally. Okay, so fairly straightforward approach. Coordinator asks for votes, or asks all the participants to vote for commit or abort, get back the votes. If all the votes are yes, you say commit. If there at least one is no, then everyone has to abort. Okay, all right. So this straightforward. The problem in this approach occurs when there are failures. Okay, and the main issue is if there is any failure, it's not possible to make a decision often without knowing what might have happened. Okay, so for example, if the coordinator crashes in the middle of a vote, okay, the participants cannot proceed because they don't know what has happened. The coordinator is essential to the process. That should be clear. Okay, but the other part is also true. If a participant crashes and does not vote, the coordinator cannot proceed either, because it's an all or nothing property, right? So it may so happen that the vote, let's take a simple example of why this might be a problem. Coordinator sends a vote request. Here's a participant that was in init. It decides to abort the transaction, okay, and it sends an abort vote back to the coordinator, but it crashes. So it makes a transition to abort, but the message never goes out for some reason because of the failure. Okay, so that participant has already aborted and the operation and got aborted. The coordinator does not hear from that participant. Okay, so it cannot actually make a decision. If everyone else had voted commit, it cannot make a decision on what to do, for example, right? So you can get blocked at many different stages in this process, and it's hard to figure out in some cases what to do. Okay, in particular, the biggest problem occurs when all of the participants have voted to commit, okay, and they're all in the ready state waiting to hear for the results of the vote, and the coordinator never returns the result because it crashes. Okay, so in this case, it's not possible for the rest of the participants to make a decision without hearing from the coordinator. Okay, particularly because the coordinator is also a process in the system. It is acting as a coordinator, but it's also a process. So you cannot have a participant ask everyone else saying, what did you vote? If all the remaining processes said we voted to commit, you can't still commit because the coordinator, which is a process in the system, may have itself voted to abort. So you cannot just make a decision without knowing what happened. Okay, so this is a problem because if you are all stuck, as the participants are all stuck in the ready state, they cannot make a decision. Okay, for example, they cannot decide the coordinator hasn't responded, let's all abort the transaction, because the coordinator may have decided the other way around. Right? So it's something that you have to keep in mind, is two-phase commit is not going to work when the presence of failures. Otherwise, it works fine. Right? So there are ways by which you can, in special cases, the participant can decide how to recover, but not in all the cases. So for example, a participant crashes and then comes back up, okay, and then it finds itself in the init state. Okay, so it's not even made a vote, so it can then actually vote and tell the coordinator to abort, for example, because if it's in init state, the coordinator could not have received it vote, so no decision. Okay. On the other hand, if it comes back up and it finds itself in the ready state, you can ask some of the other participants. If one of the participants says, okay, we got a commit vote from the coordinator, then you know that the votes were received, the decision was made, and you just didn't get the decision. It crashed before the decision came. So you can make a transition to commit. The same thing is true if at least one of the participants ends up in abort, and this failed participant that has recovered is still in ready and it finds someone else is in abort, you can make an abort. Okay? If you're in init, you make a transition to abort. The problem is if all the other participants are also in ready. If you are in ready, everyone else is in ready, you don't know what the coordinator decided. You can't make a decision. Okay? So this is the case where this protocol is actually going to suffer. Okay? So I will show you now a modification of this protocol, which is called three-phase commit, 3PC, okay, as opposed to two phases. Okay? So what this new protocol does is trying to solve the same problem. Okay? But now you have three steps. Okay? You have three steps, not two, okay, or three phases, not two, for you to actually make a decision. Okay? So here is the approach. You will see some of this looks very similar. So there's a coordinator and there are participants. Okay, the coordinator will initially ask all the participants to vote. Should this operation commit or abort? Okay, and then it will collect all the votes. Okay, now if any participant says abort, okay, that's, as I said, a veto vote. Then you send back a abort decision to all the participants. Okay, that part has not changed. So you ask for votes. You go to the wait state. If anyone says abort, then you go to send a global abort to all the participants. You're done. Okay? Now, if all the participants have said commit, okay, in this case, in the previous case, you would have just told all the participants to go ahead and commit. In this case, you will tell them to go to a pre-commit stage, okay, saying that the decision was to commit, but don't commit yet, but just go to the pre-commit state. Acknowledge that you received the decision and go to the pre-commit state. So all of the participants will then go to pre-commit. And once all the participants are in pre-commit, then you actually ask all the participants to commit through a global commit. So commit takes two steps. Abort is only one step. Okay, so that's the three-phase commit. Now you can say, what did this achieve? What did adding this extra step saying let's commit in two stages? The participants will be told to go to a pre-commit stage and then told to commit the transaction in a second step. What did that achieve for us? Any thoughts here? Okay, the question you want to think about is what problem are we trying to solve here? If you go back to the two-phase commit stage, remember I said if all the participants are stuck in the ready state and the coordinator has crashed, these participants cannot make a unilateral decision. Okay, because the participant, the coordinator would have also might have voted and done something. Right? So that's the problem we are trying to solve here. So now let's say we have this situation where all the participants find themselves in the ready state and the coordinator crashes. Okay, can we make a decision in this case? So one thing you can think about is, let's say these participants, a coordinator crashed, votes were the results of the votes were never told to us. Let's abort the transaction. This is what we said we could not do previously. Okay, so they can all move to an abort state, okay? And then if the coordinator actually recovers, the worst that could have happened at the coordinator is it would have gone to a pre-commit state. It would not have committed the operation, okay, because from a wait state you can either go to abort or pre-commit. If the coordinator also aborts, the other participants are already aborted. That's fine. They all reach the same decision. But if all of the other ones decide without the coordinator to abort, the worst that the coordinator would find is it's a pre-commit state. It can still transition out of that and abort because it hasn't committed yet. Okay? But in the two-phase commit, you could have committed and then the rest have aborted. That's an incorrect state where some of them commit, others abort. That's something you don't want. Okay? Here, because you have these two stages, you are just waiting to commit. You're not yet committed. So if others have changed their mind, not changed their mind, but gone ahead and timed out and decided to abort, this is still safe. Okay? So adding this extra stage before the commit is actually adding safety to the protocol. It prevents a situation where in the presence of crashes, some participants will go into abort and others will go into commit. That will not occur in this case. Okay? So if you find yourself, if you find yourself in the init state and the coordinator crashes, you can always abort because voting hasn't even started, so that's safe. You find yourself to be in the ready state and everyone else is in the ready state, coordinator crashes, you can still make a transition to abort because the worst that will happen is someone else is in the pre-commit stage. And if you are in the pre-commit stage, then it's okay at that point to decide what to do, because you already know that that's the vote that was sent. Okay? So this is adding an extra step, and it is adding failure resilience. Okay? That's really the problem that 3-phase commit or 3PC solves over 2-phase commit. Is this clear? Any questions here? Yes.
What if the coordinator fails after the pre-commit? Would that again lead to an...
Okay. What the question is, what if the coordinator fails after the pre-commit state, right? So pre-commit state essentially means that you have to send all of the votes to others, right? So if at least one or more participants receive that vote, they would have transitioned to pre-commit. Okay? And then if some others have not received it, they are in ready, they can check and they find somebody's in pre-commit. That basically tells you that the coordinator has actually sent out the decision to commit, which is why at least one participant is in pre-commit. So they can all transition to pre-commit and commit. Okay? So that's something you can certainly do in this case. Okay? Now you can have a case where the coordinator goes to pre-commit, but none of these decisions are conveyed to any of the participants, in which case they'll still be ready waiting for the result to come, because they are here, they never actually got the results of the vote. Okay? And I said that in this case it's safe for them to abort, okay, because at the worst is that the coordinator would be in pre-commit. When it recovers, it can check where it is and say others have aborted, so you can still abort, you're not yet committed. Okay, so you have these two cases in this case. Yes.
So this helps if the coordinator crashes, not help us if...
Question is, this helps if the coordinator crashes. That does not help if the process crashes. If a process crashes, you're right. If a process crashes and doesn't not even vote, okay, then the coordinator will be stuck, because you can only send the results after you get all the votes. Okay? There's no majority here. You have to get all the votes, because even if the remaining n-1 nodes say commit, and there's one failed process was going to abort, and you say this is majority, you cannot proceed, right? So you have to actually wait. So you're right. This is only helping from coordinator crashes. It does help with the case where the after voting, a participant can crash, and then when it comes back up, it can make a decision. But if it doesn't even vote, there is a problem, right? So that's something to keep in mind. Okay? Yes. Okay, so question is, what happens after you reach pre-commit for you to commit? So what happens after you resolve? The coordinator will send a request to all the participants and go to pre-commit stage. It will wait for an acknowledgement from all of them, because you will see that you send a ready back or an acknowledgement back. Once the acknowledgement comes, you know all the participants are in pre-commit, then you send another global commit and then ask everyone to come. Right? So the coordinator sending two messages: go to pre-commit and then go to commit, once you hear that everybody is actually acknowledged. Okay? Yes. The question is, in 2PC, couldn't the coordinator have gotten an acknowledgement to commit? So what happens here in 2PC is everyone is just voted and they go into the ready state and they're waiting, right? So at this point, you either send an abort or a commit. So that's all you do. You make a decision and you send it. And that's, if there are no crashes, that's fine, because you just get votes, you reveal the contents of the vote, right? Or the election, or it's not really an election, but you essentially vote and you reveal what has to be done, right? But the problem is, in this case, if there's a crash, there are problems, because as I mentioned, if you're all stuck in ready, you cannot make a decision. You will always be stuck in ready. That's because everyone could have voted to commit. The coordinator could have said the decision is to commit, it commits, but the votes, the messages don't go out because it crashed before the message left the machine, right? So now the coordinator is in one state and all the participants might end up at different. That's something you don't want. The question is, could you have sent the message before you make the decision? Would it have resolved the issue? I think generally you want to first write out your decision to disk before you send out messages, because if you send the messages and don't take a decision and you crash, and then you come back up, you don't even know what decision was made, right? So typically you will write the decision to a log and then send it out so that if there's a crash, you know what is written in the log, what has happened so far. So because there's a disk log that's not shown here that has to be maintained, that's why you have to do it that way. Okay? Yeah, if you do it the opposite way, there are other problems. Okay? All right. So what we'll now do is say this is too problematic. Okay? We don't want this situation where you have to wait for everyone to vote. Okay? Let's actually relax this and say we want a technique that allows us to make a decision in the presence of some failed participants. So long as a majority of them are up, okay, the coordinator should be able to make a decision. Okay? How do we do that? Okay? So that's what we look at. That's called consensus, and we'll look at paxos. So you'll see some similarities, but the main difference is two-phase commit and a three-phase commit really are not designed to handle failures. In some special cases, they can deal with it, but not in all cases. They'll always have some problem or the other. But paxos and consensus protocols that we'll see are fundamentally designed to work with a majority. Even if a minority of nodes have failed, you can make progress. Okay? So that's really what we are going to look at. So that brings us to back to replication and consensus. So remember two classes ago, I talked about replication as a way to implement fault tolerance. So I said you have multiple replicas. If some of them fail, the others can take over. Right? So that was the main idea for replication. Okay? And typically when you have applications being replicated, okay, you use replication in one of two ways. You use it to get scalability, where the incoming workload is split across replicas, and you can spread the load, but if one replica fails, the other can take over. Right? So you're getting fault tolerance and some way to actually distribute the load. And the second approach for implementing fault tolerance, which is what we are talking about, is you always send the request to all the replicas. Okay? You take a majority vote, okay? And then the result is what is sent back. So this is the other way to do replication, where every request is sent to all. In the previous case, the request is sent to one of the replicas, they execute it and send back. Here you send it to all, you get back the results, you take a majority result, or you have them vote on all of them. And so that's what we did for 3PC and 2PC. But now we'll look at how do you deal with just a majority, not all of them. Okay? So that's the other approach we are going to look at, which brings us to this topic of consensus. Okay? What is consensus? Consensus simply means a group of processes in a distributed system have to agree on something. Okay? What they're agreeing on is really not important. That's orthogonal to consensus. So you could be agreeing on what is the result of a database query. Okay? You could be agreeing on what's the output of a remote procedure call. You could be agreeing on in what order should we execute these requests. Okay? Or you could be agreeing on should we commit or abort the transaction. That's what two-phase and three-phase commit were doing. So what you're trying to agree on is actually orthogonal to the consensus protocol. The consensus protocol just says that these processes need to figure something out. Okay? Whether it's the output of a operation or whether to commit the transaction. They're just trying to figure out what to do. And the consensus protocol will all let them agree on what is the right thing to do. Okay? So that's essentially what consensus means. So consensus protocols generally assume that processes can fail. Okay? And they may not actually participate in the consensus protocol when they have failed. Okay? Yet you want to reach consensus. Okay? But they do not assume that you will produce wrong result. Okay? So we'll assume that processes are actually operating correctly when they're up, or they fail, in which case they don't actually participate at all. Okay? Now there is a version of consensus called Byzantine agreement, also sometimes called Byzantine consensus. Okay? This is like the Byzantine general problem where you are trying to be part of a consensus protocol, but you may maliciously provide wrong input to the protocol to confuse other processes. Okay? And yet you want to reach agreement, okay? Or yet you want to reach consensus. So if you want to agree on something where some processes are Byzantine faulty, that gets us into Byzantine consensus. Okay? But if you want consensus where you only tolerate crash failures or maybe network failures, but you're not assuming that processes are intentionally sending wrong result, your traditional consensus. Okay? So we are going to only talk about traditional consensus today. Right? Eventually, we'll get to cryptocurrencies, where, as I said, you actually need Byzantine consensus or Byzantine agreement, because you assume that participants are actually faulty or malicious. They are trying to do bad things. Okay? Here, we are assuming you are not trying to do something malicious, but you can fail. You can just crash. Okay? So that's what consensus means. So remember that for today's class, okay, all processes, when they are operating, are just producing right results. Okay? They are not trying to provide bad or faulty results. So either a process can be up, in which case it's functioning correctly, or it can have crashed, which means it's not part of the system. So these are the only two states, okay, that we are going to worry about. Okay? So we want essentially 4 properties from our consensus protocol with crash, or what's also called fail, stop, failure. First is agreement. Agreement says all processes are going to end up with the same value. Okay? This was the same thing as everybody commits or everybody aborts, right? So they should all agree on the same value. Termination essentially means that every process actually ends up with a value. It's not hung forever, right? So you're not going to be in a state where you make no progress. So you want the process to terminate. You want everyone to agree. Validity says that you should essentially pick a right value. You shouldn't pick a random value. Okay? Because a trivial consensus protocol is every time you run the consensus protocol, everybody decides false is the answer. Right? It's not a very useful protocol, but you always get agreement because you a priori determine that every time you run it, we'll say the answer is 0 or answer is false. But that's not valid values. You want to actually pick something that's valid output of the operation. And integrity says that every correct process decides the value, everyone has, somebody should have actually produced that value, right? That should have been an output of a database query. That's what we are agreeing on, because you don't want to agree on something that's wrong. Okay. So these are not the same as ACID properties, but they're somewhat like that. Your agreement, termination, validity, and integrity. But we really are not going to get into the nuances of this. We'll just think about, we want to reach agreement, that we want all the processes to essentially agree on the same value, and we'll assume the value is valid. Okay? So let's try to understand how to do this. But before we get to paxos, I just want to reiterate the problems with 2-phase commit and 3-phase commit. Okay, so what you want to understand from 2-phase and 3-phase commit are, there are 2 properties that you would like in a typical distributed system or application. One is called a safety property. Okay? The other is called a liveness property. Okay? Safety property, the way you want to think about safety is, safety means nothing bad happens. Okay? That's a safety property. If you have a safety property in your system, that means that the system will not do something bad. Okay? What bad means will change from situation to situation, but you will not do something bad. Okay? And liveness property means something good happens, that you make progress. Okay? So that's what liveness means. Okay? So if you go back to 2-phase commit, okay, you will see that they have both they have safety property but not liveness property. Safety property essentially means in 2-phase commit, what does bad mean in this case, right? In case of 2-phase commit, bad means you don't want some processes to end up with an abort and some with a commit. So then you violated atomicity. Okay? And you'll see when I talked about it, I explained to you that you always end up in the right state because you give up liveness. You say that we would rather hang forever and not make progress because the coordinator has crashed, because making a unilateral decision might violate safety. You might end up in the wrong state from the coordinator, and then you have violated atomicity. Right? So you gave up liveness in order to ensure safety. Ideally, you want both. You don't want to say that I will give up safety and make progress, or I will not have safety but not make progress. But the problem with 2-phase and 3-phase commit is that they are safe. They're never going to give you incorrect result, but sometimes they'll give you no result at all because they're trying to ensure safety and will not make any progress in the interest of safety. Okay? So what paxos will do is it will give you safety, but it will also guarantee liveness when a minority of nodes have failed or some network failures has taken offline a minority of nodes. Okay? So long as the majority is still functioning, okay, we will make progress. We'll have liveness, but safety is also still there in that system. That's what we are trying to actually go for. Okay? So that brings us to paxos, which is agreement in the presence of failures. Okay? So here, I mean, what the agreement is, as I said, depends on the situation. You can agree on who is the leader. You can agree on which is the most recent request. You can agree on what should be the result of this database query. You can try to get agreement on should you commit or abort the transaction. So those are all things or types of things you might want to have agreement on. Okay? Paxos will essentially not care about what it is what you're trying to agree, but it'll tell you, give you a mechanism to actually reach agreement. So that's the basic idea. Okay? So I'll show you example which will explain how Paxos works. But the basic idea is not very different from two-phase and three-phase commit. Okay? We will have a leader, that's like the coordinator. Okay? We'll have a set of follower. Okay? The goal of the leader is to convince the followers on what to do. Okay? And it will essentially use techniques like voting to figure out what the right thing to do is. Okay? And we will see that there are three phases in this case, and you will get to agreement at the end of three phases. I should mention that this Paxos technique was independently proposed by Lampert. We've seen Lampert several times now, and Liskov, who is a faculty member at MIT, maybe 2 or 3 decades ago. And it's now a technique that's used in many industrial systems like Zookeeper, Chubby. We'll encounter some of this in upcoming classes. Okay? But let's talk about Paxos. Okay. We want safety and we want liveness. I'm not going to get into a lot of these details, but let me show you an example. Okay, just to explain how this is going to work. Okay, so assume this following situation. Okay, there's a leader that's been elected in the system that's going to act as like the coordinator, and then there are other nodes which we will call acceptors in this case. They're really followers, but they're acceptors. The goal of the leader is to convince all the acceptors to accept the same value or the same output so that they reach agreement. Okay? So in this case, in this example, we'll assume that they have to agree on some numeric value. Maybe you made an RPC request. The RPC request returned 2. Everybody has to agree that the output of the RPC request was 2. That's what we are trying to reach agreement on. Okay? But what you agree on could vary from situation to situation. So initially, we'll assume client makes the request, RPC request, comes to the leader sends it to all of the acceptors, they execute the request. Now they all have to agree what was the output, okay, just to make sure they all agree on the same thing. So here is how it's going to work. Okay, so essentially, we will have rounds. Each round is called a proposal, and proposals are numbered, okay, because it may take us multiple rounds before we actually converge to a decision. Okay? So each time, the goal, the leader will start a new round. It will have a new proposal. It will try to get all of the acceptors to agree. If it is succeeded, then it's done. If not, he'll start a new round and get them to agree again, and so on. And the reason you need multiple rounds is some nodes may fail, they may not respond, or a majority of nodes may not respond, and the acceptor has to say, okay, I didn't get any results, so I'm going to restart Paxos and try this all over again. So you'll keep trying until you essentially converge. Okay, so in step 1, it's going to ask all of the acceptors saying, what should we do? What should we agree on? So it's going to send, the way you do this is you'll send a prepare request and say, this is round 1. This is proposal number 1. Okay, this is a prepare request, means you tell me what value we should agree on. Okay, so initially, and each of these will keep track of the latest proposal they've heard. So initially, they're all 0. None of them have agreed to anything. So the value they've agreed to is null, okay, because we just started this. Right? So this is what will happen. Okay? So the first round, they will all say, I don't have a value. I'm just going to say null is the value I know. Okay, so I'm going to send an acknowledgement. That's prepare OK, saying I acknowledge that we are in proposal number 1, but I don't have a value. My value is null. So that's what it's going to send, because they don't have any value that they've agreed to yet. Okay, so at the end of the first round, all that has happened is they all acknowledge that the round started, but there's no value they have proposed yet. Okay, so what the leader will do is it will take all of these. If all of them are null, it can propose a value. It can say, I also executed this RPC request. The value was 2, so it can get them to agree on it. Okay? If some of them have sent that value, it can also pick there. But as of now, you just got nulls. Is this clear so far? Okay. So now the leader is saying, everyone said null. My output of RPC was 2. I'm going to get everyone to agree on 2. So it's going to try to say, let's accept 2. So it is essentially going to start the next phase saying, okay, we started the prepare. Now here's the accept phase. Okay, still round 1. I propose value number 2. Value is 2. It's going to send this out. Okay. So the simplest case is nothing, no one has failed, right? So all the machines are up. So they will essentially all say, okay, they will take the proposal number is 1. They will all turn the null value saying, okay, I agree to 2. Okay. Because as I said, when machines are up, they function correctly. So if the RPC at the leader returned 2, all of them should have gotten that same value, okay? Because we are assuming correct execution. Okay. So they should all agree to 2. So they will say accepted value is 2, and they'll just send an accept saying I agree. Okay. So that's it. And then you have the final phase where the leader says, I got a majority of them to agree to 2 because they all sent me an acknowledgement. So he'll say, let's decide on 2. Okay, so he'll send a decide request saying we all decided that the value that we have, that output of this RPC is 2, and you send back a 2, and then that's it. Okay. It almost sounds trivial, but it actually has lots of subtlety. So let me repeat what we did here. We had 3 phases. The initial phase, you ask all the nodes, what should we do? You start a round and you say, what should we do? Initially, no one has any values they've accepted, so they will essentially just say null. Okay, and then the leader will pick the value in this case. Okay, in this, because if it all gets null, it can pick a non-null value and say, let's pick 2, sends it out. If they all or majority of them say okay, you just say decide on 2. Okay, this is a simple case, no failure, so it's fairly straightforward to understand what's going on. Yes.
If the leader says 2, but the rest of the followers, none of them have 2 as a value, then also we decide on 2, or do we at least have a 2?
Okay. Question is, if the leader says 2, but none of the followers have 2, should we accept it or not? So you will see the nulls here means what is there with the follower. Okay. So the agreement phase, you are going to take the computation, keep it aside. You're just agreeing on what to do. So you will essentially initially have nulls. Whatever is proposed, you will accept it. Okay. And then from that point on, you accept it. And if you are asked what have you accepted, you will return 2. Right. So the goal is for the leader to tell everyone what we need to agree on is 2 is the output of our computation. Okay. So everyone starts with null and someone proposes 2. In this case, the leader proposes 2. Okay. There's a generalization of this where any of the acceptors could have proposed 2, and then that propagates out. I gave the simple case where the acceptors always have null. They send null, the leader picks and tells them what to do. But it's okay in Paxos for one of them to have proposed that value initially. You go to the leader, it will send it back. Okay. All right. Any other questions? We are going to look at the failure case next. Okay. So we will now assume that in the midst of that process, there is some failure. Okay. So here is the example. So when the accept went out, we'll assume that only one of the node actually acknowledged that accept. Okay. It got 2. Okay. And it said fine. And then there was a network fault and A2 and A3 never responded. That's a majority failure because 2 out of the 3 nodes are not responding. Okay. So this round is going to fail because the leader cannot proceed. Okay. If 2 out of the 3 had responded, that would have been okay. The leader would have then left this A3 out and it would have sent the result saying the result is. But in this case, 2 have actually gone down. So majority has failed. So we cannot proceed with this round. So essentially the leader will time out. It will keep waiting for A2, A3. And after the timeout expires, it will start a new round. Okay. Hopefully A2 and A3 would have rebooted by then. If not, then this will just keep repeating until at least the majority of the nodes are back online. Otherwise, you cannot proceed. Okay. So majority have to be up, otherwise system doesn't work. Okay. So let's assume now that A2 and A3 are back up. Okay. So we are going to restart the entire process. Okay. But now, so you'll start again with, let's start with the prepare request and say this is round 2, proposal number 2. Okay. And now you can see that A1 has already accepted 2 from a previous round, okay, because it actually got the accept request. A2 and A3 were that ones that failed. So A2 and A3 still have null. So leader has already convinced A1 to accept 2, but A2 and A3 haven't. accepted anything yet. Okay, so it's basically saying what should we do, which is a prepare request, goes to all of them. Okay, so you will see now that A1 is going to say I already accepted 2, so it's round 2, its value will be 2. A2 and A3 will return null. So we haven't accepted a value yet. Is that clear? What I just said? Okay. So A2, so now the leader is going to get 2 from A1 and nulls from A2 and A3. Okay. You'll still pick 2. Okay. And then you'll say, let's accept 2, and it's going to send, here's round 2, let's accept 2. We'll send it back, okay, to all of them. So in this case, let's say there are no failures. So they all get this request. Okay. And then they will basically send an accept, okay, and you'll see that they all updated the accepted value to 2 from nulls. Okay. So in this case, now leader actually told everyone, they all said fine, okay, and then they sent an acknowledgement, and then they had the final decision request saying, okay, we decided the accepted values 2. Okay, there's a simple failure case. There could be arbitrary failures in paxos. Leader might fail, which I didn't show. I just showed a network failure. Leader fails, you have to elect a new leader, okay, and then restart that process, and then it will start the same thing again. Okay, participants, a minority of participants can fail. That's okay. If minority fails, that whole process will continue as is, because so long as 2 out of the 3 are responding, the leader can continue to make progress. That's majority vote. Okay, but if majority go down, the round fails and you have to restart. Okay, leader goes down, round fails, you have to re-elect a new leader, and it will start paxos all over again. Okay, so lots of things can go wrong, but because we can proceed with the majority, unlike 2-phase commit and 3-phase commit, we can reach agreement with the majority of the nodes being up. Is that clear? Any questions? Yes.
If a node fails, it got rebooted, but by the time it gets rebooted, the proposal has already been rebooted. So what happens to the
Okay. Question is, if a node fails and by the time it gets it reboots, that proposal has already been accepted, a decision has been made, right? So you can always go back to the leader and say that tell me the if that round has concluded, you can catch up later. We will see exactly that in RAFT. Okay? So you basically, maybe A3 goes down for an hour. Several operations happen in that 1 hour. When it comes back up, it can go back and read the log from any of them saying, tell me whatever I have missed, and it can just replay. There's no need to redo anything. You're just asking what happened. Just tell me what was decided, because the majority decided it, so it'll just have to get the decision from someone else. Okay? Yes. Okay. Question is, if in the second proposal, what has come back from A1, A2, A3 is 2 null, null. Okay. So what is the leader trying to accept? Is that your question? The leader has to always accept a non-null value, a value that was actually produced by an operation. The operation produced 2, it should not accept null, because that was one of the properties of consensus, saying you could always accept null. There's nothing to do. Right? I can always say every consensus operation outputs null. So I don't actually have to ask anyone. I say, here, let's decide on null. So that's not a useful protocol. You want a protocol to accept a value that was actually produced by the computation, which I said, let's say the gRPC returned 2. So technically, in this case, you should accept 2, not null. Okay. So question is, if I get 2 null, null, there are 2 nulls and 2. Why is the leader accepting 2? That's your question, right? So in this case, we are not actually having a majority vote to decide. Okay. The majority have to be participating in the paxos protocol. So it's not like they're voting. It's not like you will vote 2, 2, 3, and then you vote pick 2, because there is no crashes, right? So you always assume that you will have the right output. So it's not a majority of what has been reported to you, okay? But the majority have to be participating. And so long as there is even one non-null value, that's the correct result of the operation. That's what you have to now convince the rest to actually agree on. Okay? So it's a little different from assuming, unlike 2-phase commit, where you say, should we vote or not? You get all of them and you take a look at the result. That's not what we are trying to do. You're not trying to take the 2 out of 3 of what to accept, but you want all of them to respond and say, I agree to whatever you're telling. Okay, is that clear? Yes. Are there what? Okay, question is, are there any rules on how many replicas you need? So you need, in this case, this is the simplest case, you will need at least 2 so that there is a majority, right? But you can have any arbitrary number. So long as you have n plus, let's say, if you have n replicas, you need strictly greater than half to be up. That's all you need, right? So you need, if you can't have 2, because then if one of them goes on, that's not a strict majority. But if you have 3, then you know that at least 2 are up. So it's greater than half. Right? So the only rules are you need out of n replicas, strict majority. Half plus 1, at least that many replicas have to be up. Okay, yes. The last picture, the question is the last picture where you say decide, is that proposal 2 or 3? That's just the last phase of the current round. There are 3 phases. There's an accept phase, which is asking, propose phase, which is saying, propose a value, what should we decide? There's an accept phase saying, let's accept this value. There's a decide phase saying we decided on the value. So this is still the same round. It's not a new round. Okay. All right. So I think I'm going to actually show you the protocol now. So this is just explaining in pseudocode whatever I explained. So step 1, phase 1 is the prepare phase. This is where the leader is going to start a new round and is going to send a prepare request and a round number to all the nodes. Okay. Upon receiving a prepare request, okay, you essentially, if a new round has already started because this replica is really slow and maybe a new round started and you never actually responded to a previous round request, you can just say, I got a new request already, a new round has started, so I'm going to send a reject. I didn't show this case in the example because this is only going to happen where you have some replica that failed and recovered, or a replica that's really far away where messages reach them out of order. Okay? So maybe the previous round message reached after a new round started because the coordinator timed out and then he started a new round and then the previous round request started. And then you can just say, I already saw a higher proposal number, new round has started, so this round must be already over by now. So you just send a reject and send a cleanup message. Otherwise, you will basically send, this is the current round number. I'm going to essentially, if you accepted a value, you will send that. Otherwise, that value will be null. Okay. So if you are, this is a subsequent round, initially it will be null. Okay. But if you already accepted something from the previous round, you just report that back, that you already accepted. Okay. So that's the phase 2, which is the accept phase. If the leader gets a prepare OK or an acknowledgement from majority, okay, it will start with the prepare phase. Otherwise, you will time out and restart the first. Okay. So you will take all the values that came back. Okay. If all of them are null, okay, leader picks the value. If any of them is non-null, you can pick that value. Okay, because you know that's something you proposed previously and was accepted, so you'll pick that value. Okay. And then you will send an accept request with the round number and that value to all the nodes. Okay. And then, of course, if you don't have majority, you restart. But now a participant, when they get the accept request, they're essentially going to update their values and send an acknowledgement. Okay. Of course, if you have previous round, then you say, this is an old round, I'm not going to take this. There's a new round that started. So every time you have to check if this is the latest round. Otherwise, old messages are coming because of out of order delivery or the network got blocked and sent a message late, you will reject that message. Okay, so you want to have strictly increasing round numbers. Old messages are always discarded. Okay. And step 3 is phase 3 is the decide round. This is where everybody is already majority have agreed. So you simply send a decide request with the value. It's sent to all the acceptors. And you might have other nodes that are not participating in paxos. It's not required that every node that's a replica has to participate in paxos. You can have a subgroup that's deciding what to do and everybody else is told. So you might have nodes called learners that are just not participating, but they want to know what was decided. Okay? So the trivial case is where all nodes are participating, they're all acceptors, but the special case is if your large number of nodes, some smaller group is actually running paxos and telling everyone what the outcome was. So you will send this value not just to the acceptors, which is what I showed, but any other node in the system that needs to know what happened. Okay? Yes. Okay, question is, what happens if this decision fails, right? So in this case, if you don't get an acknowledgement saying a message was received, again, this will fail and you will restart. At any point, if you don't get an acknowledgement, you will have to restart from majority. Right? If you get from majority, that's okay. Minority may not have to respond. Okay, so you will see here what you just asked. If you do not get an acknowledgement, you will delay and restart paxos. Okay, so that's going to happen as well. Is this clear? Okay. So there are many properties that I will not prove here, but what we have to ensure is each round number is unique. It keeps increasing. Okay. And you have to ensure that when there are acceptors in a cross round, there's at least one node in common. That's true because if you have majority vote, okay, when you have two majorities with different numbers of nodes failing, the intersection will have at least one common node. So you will ensure that if at least one node is common across majorities in different rounds, you will still end up with the same result because you would have, some of those would have accepted a value. Okay? And then the value, essentially, you have to make sure that you always take the highest number proposal and agree to that. You should not agree to something from a previous proposal because that proposed round would have already timed out and failed. So you want to make sure you always take the highest numbered proposal or the latest round, and that's what you agree to. Okay? So these are all properties to ensure no failures, or not no failures. There are failures, but you want to make progress in the presence of failure. Okay? Now, there are lots of use cases you can think of, right, as to what might go wrong. Network partitions, I already showed you an actual example. So long as there's a majority on one side of the partition, okay, you can continue to run, right? The case I didn't show you is in this example I showed you, maybe there are 10 nodes, okay, 9 of them disappear and only one of them actually goes to this leader. This leader can wait for those nodes to come back, but an alternative is those other 9 nodes can pick their own leader and they can make progress because you have a majority on the other side of the network partition, right? So you cut the network into 2, 9 of them are on this side and the leader and 1 of them are on one side. Okay, so this option showed you the leader is just waiting and those nodes rejoin, but maybe they won't for a while, but those other 9 nodes can pick their own leader. They still have a majority and can make progress, right? So that's another thing that I didn't show you. So, but that can happen. So you can have majority on any one side can essentially continue to make progress. If there's a timeout, some node doesn't respond, it's slow, you can essentially restart paxos, you can elect new leaders and so on. What you want is essentially if there are 2 leaders, you don't want bad things to happen, but that will not be the case because you will always have a majority on one side. So why would you have 2 leaders is exactly this case I just explained to you. Maybe there are 10 of these acceptors, there's a network partition, 9 of them are on one side, there's one acceptor and one leader are on this side. Those 9 select their own leaders. Now you have 2 leaders in the network, right? There's a leader with a minority partition and a leader in the majority partition. Okay? Now, by definition, the leader in the minority partition cannot make progress because it's not getting responses from the majority, but the other leader is making progress. Okay? So when the network heals again, you want to make sure that there's still again one leader and they made the right decision. So you have to have some of these additional techniques because you might have partitions, you might have end up with multiple leaders, the network comes back, now you have 2 leaders, what do? You want to make sure all of those cases are handled. Okay? But the good part is because only one partition can have a majority, only one leader that will actually make progress, others will just sit there and keep timing out. Is that clear? Okay. So lots of failure cases like this, which I will not go into a lot of details, but you kind of get the idea why you have to deal with them. But because we always stick with the majority vote, we are guaranteed that only one leader can make progress. That's the basic idea. Yes. Okay. Is it possible both partitions don't have majority? Yes. You might have some node that simply crash, right? The example of 10 nodes, let's say 5 of them crash. Okay? 2 of them end up on one side, 3 of them end up on another side. There's a crash and a network partition. There is no majority. There's no majority, there's no progress. Okay? The basic rule is there has to be a majority to make progress. If you don't even have a majority, there is no progress. Yes, you can have network partition where there's no majority on either side, because in addition to the partition, some node just failed. Yes, then you cannot do anything in that case. Okay, so that's paxos. We'll now see another protocol called RAFT. Okay, so this is a different consensus protocol. It's trying to do the same high level thing. You're trying to get agreement. Okay, but this one has a different way on how to do agreement, because RAFT is trying to reach agreement on only one thing. Okay, and that thing is there are multiple requests coming into the system. Let's agree on the order in which the request entered the system. Okay, you're not agreeing on what is the output of an RPC operation. You're not agreeing on should we commit the transaction, abort the transaction. Paxos is the more general case where you can agree on anything. In RAFT, you're specifically trying to agree on requests are coming into the system. There are multiple replicas. All the replicas need to agree on the order in which they entered the system. Okay? So if you say there are 3 requests, A, B, and C, all of them say A came in first, B came in, C came. If they all agree, that's what we are trying to reach agreement on. Some ordering. Okay? And the ordering specifically is the order in which requests are out, and we'll see why that is the case. So some people think RAFT is an easier protocol to achieve consensus because you'll see that some of this is easier. You're not having multiple rounds and so on, but it has its own nuances as well. Okay? Now RAFT, the main thing the reason I wanted to mention RAFT is RAFT essentially implements consensus on what's called state machine replication, or SMR. Okay? And I'll explain what SMR means. Okay? So the basic idea in state machine replication, the name seems fancy, but the basic idea is very simple. In fact, let me show you a figure. Okay? Here's the figure. So initially there's a left side of the figure and a right side of the figure. Let's just take the left side. Okay? So we will assume that there are some number of replicas. Okay? In this case, requests come in, they're sent to all the replicas. Okay? And you want the replicas to execute the request in the same order. Okay? So remember the database example I explained way back when, where there are 2 queries coming in. One database replica gets query A followed by B, the other gets B followed by A. If they execute them in 2 different orders, the database state may be incorrect. Okay? So you want to keep the state the same. If all the replicas are identical, have the exact same state, and you have a set of requests, you execute all the requests at the replicas in the exact same order, the final state should also be the same. Because each state is only modifying that, let's say, the database in some way. Right? So you want to ensure that all the replicas are going to execute requests in the same order. Then all the replicas will always be identical in terms of their state. That's the basic question. Now, how do you do this? Essentially, what you do is you essentially keep a log. The log essentially just keeps the requests in the order you're executing. Right? So here is an example of a log which says, okay, so the log says I executed a request which assigned 3 to the value x, then I executed a request that assigned 2 to the value y, then I updated x to 1 and updated z to 6. These are all requests that are coming in there, updating database records, which are x, y, z, and the number is what it has been updated to. Okay? So you just have this log that says, I received this request, each request made the following operation, I have kept this log. Okay? Every database actually keeps this log anyway. If you think about the redo log that I was explaining when we talked about transaction, all these logs are already maintained. Okay? Now, the point is, since there are multiple replicas, if they get these requests out of order, okay, and you execute them in different orders, you might end up with different states. Okay? So you want to make sure all of them are going to execute them in the same order. The way we are going to do this is that we are first going to insert the request into the log, okay? And then the database will take each request from the log and replay it and say, this is what I'm going to do. Okay? And if the logs are identical on all the machines, it follows that you are simply taking a next request from the log, executing it. So the idea is you want to make sure the logs are consistent, and then each database or each replica is just pulling the next request from the log and blindly replaying it. And then so long as you start with the same state, you execute the same request in the same order, you'll end up with the same state. So all your replicas will always be consistent. Okay? So the state here is the log. Okay? And when we say state machine replication, we are simply trying to replicate the log. That's all we are trying to do. We want to make sure the same log is on the machine, all machines, and it's identical. And then all these machines are simply pulling requests from the log and executing it. Okay? So our consensus problem has reduced to keeping a log on each machine. A log is a file on each machine and ensuring that the file contents are identical across machine. That's the problem we are going to solve. Okay? Rather than all this paxos-like protocol, we just want now to make sure there is a log on each machine, and each machine has the same log, same request in this log. Okay? And again, you can have crashes. Some machines might disappear and come back. Okay? And then their log is out of date. Then it has to resynchronize the log. So we want to make sure that even though some minority machines have gone offline, come back, we always make sure the log is identical. Okay? We recover to the same state. Is that clear? Okay? This is called state machine replication. The state machine is basically a term for a log. So it's essentially log replication. Okay? And we want to ensure consistent log replication. That allows us to ensure that all of these machines have agreement on what order to play requests. Is that clear? What I'm saying here? All right. So let's talk about how this is going to work. Okay? So we will essentially assume a leader-based consensus protocol, which is RAFT. So there will be a leader. Okay? So what will happen is requests will come to the leader. The leader will first put that request into its log. Okay? Now the leader has a log. It's updated the log, and its goal is to tell all of its followers saying, okay, now here's an update you need to make to your log. So your log and my log are identical. Okay? So all the requests will come to the leader. The leader will decide on the order. Okay? And it will start inserting these requests into the log. That's the order in which all the replicas have to put them in their log, and that's the order in which all the replicas will execute those requests. It doesn't matter what order they receive the request, they have to execute the request in the order that the leader tells them to execute. Is this clear? Okay. All right. So we'll first essentially pick a leader, and then here's how it's going to work. Right? So we'll assume that time is divided into terms. Terms are like rounds. Okay? In each round, you will have a leader. Okay? And then in that round, it's the job of the leader to tell the followers what order to put requests into the log and what order to replay those requests. Okay? Across rounds or terms, there can be election. A new leader may be elected. Okay? Because maybe the leader failed, maybe the leader said, I'm done, go pick a new leader. Why the leader stopped being a leader is not our concern, but we'll assume that so long as the leader is stable, you have a round. When the leader disappears, a new round starts. So new round has to start with a new leader election. Okay? We know how to do leader elections, so I'm not going to talk about that. I'm going to talk about what happens after a leader is chosen in the green phase where you are doing log replication. Is that clear? Your question? All right. So here, let me show you an example. So we will assume that in the leader election, we'll assume that if you have essentially no RPCs received for maybe half a second, there are no messages in the system for half a second, you assume leader failed. Okay? And you start a new leader election. Why half a second? That's what the designers picked. Okay, you could have picked some other value saying if I haven't heard from the leader for some duration D, you assume the leader failed, you pick a new leader. Here the duration is somewhere between 100 to 500 milliseconds. Okay? So, and then you pick a leader. We won't really worry about how to choose a leader. We did that already several classes ago. But now let's look at how normal operation works. Okay? Leader is going to receive requests from the client. Okay? It's going to receive requests. So let's say leader is just a database, right? It's going to receive queries from the client. It is going to insert these queries into its log. Here is the leader's log. Okay? So you will see that each request, each entry in the query is numbered 1 through 8. Okay? The colors here stand for a term. Okay? So the green term had a green leader. Then that leader maybe decided not to be leader. Then a new term started, which is yellow term. There's a new leader. Now we are in the purple term. This is the current leader. Okay? So it's now adding it. So leaders will change over time. Okay? And now this is the log of the current leader. Its goal is to make sure all the followers have exactly that log. That's all we are trying to achieve here. Okay? So essentially what's it going to do? It's going to first enter the newest entry into the log, okay, which let's say is x is 4. Okay? So it'll do an append entry, and then it will send the RPC to all of its followers saying, go add that entry. Okay? To get an acknowledgement, you are done. All of them, the majority said, yes, we added it, so you have consensus. So you said, I added this entry, my majority of my followers added this entry, we are done. Okay? And if majority hasn't actually acknowledged, then maybe you have to start a new round, okay? Or you have to retry. So now the problem comes when some followers have failed, and then they come back up and they find that their log is very different from the leader's log because they didn't receive some of these entries, they had failed. So you have to essentially reconstruct that log. So this is the example. Excuse me. So here is an example where a follower came back up. It has 4 green entries, okay? And here is the leader. The leader has 3 green entries, 1 yellow entry, 1 blue entry. Okay? So it has to essentially repair the log at the follower because this follower has an incorrect entry and it is missing 2 entries, the yellow and the blue one. Okay? So we'll see how to do that. Okay? And here are other examples. Okay? That the top one is the leader. Okay? You will see that it has a yellow, green, yellow, pink, and blue terms, right? And you will see that these followers have all kinds of problems. Okay? This follower has 1 missing entry. This follower has several missing entries. Okay? These followers are extraneous entries. Okay? This follower seems to have a term where nobody else has seen it. Maybe it got partitioned, it picked some leader, it added some entries and then disappeared. Right? So this has extraneous entries. These have also extraneous entries and so on. Okay? So you can have all kinds of problems. So when a follower comes up, it might have missing entries. It may have entries that the leader never agreed to that are just extraneous that have to be discarded. Okay? So you have to do log repair. Okay? So essentially the question is, how are we going to do log repair? What's the simplest way we can do log repair? Go ahead. Yes, you have to take the leader's log and sync it. So let's take the missing entries case. Okay. So what's the simplest way you're going to sync a log of the leader with a follower log that's missing some entries in the suffix? The prefix is the same, the suffix is missing some entries. What should we do? How are we going to sync? What's the simplest thing you can do to sync this? You can replace the entire thing. That's simple, definitely simple, but less efficient. Yes, I should say simplest but efficient thing to do. Yeah, you could just have the leader send the entire log, but logs might be quite long. So maybe you want to do something little more efficient than that, right? Yes.
Like ask for logs after a particular time.
Okay, so you can ask for log after a particular timestamp and say you'll replay that. You could do that. Okay. So another thing you could do is you start with the most recent entry in the log, leader log, and you keep rewinding the log until you find a matching entry. So then you know how many entries are missing. So the leader might say, do you have entry 10? You'll say no. Do you have entry 9? You'll say yes. So then you say, okay, you are missing entry 10, so you will send that missing entry. Okay? So essentially you can do a diff. Rather than sending the whole log, you can do a diff saying what is the prefix you have. You find that and then you replay all the remaining entries because you know the follower doesn't have. So in case of follower B, you will go all the way to entry 4, and then you will basically send the remainder of the log. Okay. Now, when you have extraneous entries, you have to do extra work. Okay. You have to ask it to throw out those entries and then also find the prefix that matches and then go forward. So in this case, in C, you just have an extra entry 11, which is not there at the leader. So you might have to tell it to go all the way back to 10, and then you reach the prefix, there's nothing. So you just have to delete that 6 there. Okay? And in this case, you have to delete these 2 brown-looking entries saying you seem to have some extraneous entry, throw them out. Right? So essentially, you want to find an efficient way to go backwards until you find a match, and then make sure all the entries that are missing are either sent or the extraneous entries are deleted, or both, because you might have some missing entries, some extraneous entries. Okay? Once you do this, then these logs of the followers are repaired, and then they can rejoin the RAFT protocol where they can start adding entries to the log. Okay. So the simplest case is where there are no problems, all the followers are consistent, new request comes in, leader adds it to its log. Now there's an extra entry, right? And then it has to tell the followers to add that same entry. It will send an RPC saying add this entry. They'll all add the entry, send an acknowledgement. You're done, right? Because you just added an entry, now everybody is synced up. Okay. The more problematic case is some followers are, because you're doing majority still, right? So long as the majority say they're done, you're still done. But the minority that didn't respond will now have inconsistency in their log. So when they rejoin, they have to essentially resync their log. Okay, there were some questions here. You had a question and somebody else had a question. Okay, question is the follower has a bad entry. Why are we discarding it? So in this case, the goal is that you have to take the leader's log and you have to replicate it, right? Where this extraneous entry came, we don't know. For example, it may have so happened that the reason you have this extraneous entry is this node was a leader. Okay? It essentially added 2 entries into its log and it sent an RPC request to all the other followers to add it, but then it crashed before it could make all of the nodes. So now it has 2 entries in its log, okay? Because it was a follower at one point, but it never got the others. Oh, sorry, it was a leader at one point, but it never got its follower to accept it. So then you have to remove those entries, right? So that's why you might end up with these entries, because as I said, the first thing is when a request comes in, you add it to your log. Then you have to convince others to add it to their log. So in this case will happen where you are a leader, you entered something, but you couldn't get others to agree. That's one example. Okay, question is how do you deal with losing that particular entry? So in this case, you just remove that request and eventually the client will get a timeout saying the request did not succeed. Okay? Because you could not get agreement. Yes, there's some question here in the case.
Is there a possibility of having some experience that having
Okay, question is there a possibility of having an extraneous entry and then a correct entry? That's your exam question, right? So technically, you shouldn't have a case where the middle of the log is the problem. Okay? If you do this protocol right, the prefix should always be right, and it should be either you're missing entries in the suffix or your extraneous entry. If you have the middle that's problematic, then you cannot just go back to the most recent correct entry and play it out. Okay? And the reason, again, why you will not have the middle entries to be wrong is if the follower comes back up, it's not allowed to add new entries to the log until it is synchronized. So only way what you said will happen is you are already entering entries, new entries to the log, valid entries when you haven't repaired your log. So if you add entries to a bad log, then you will have that case. But we are assuming that you will make sure the log has been repaired before you allow to add entries. So you shouldn't have that case. Okay, there's some question there. Okay, any other question? Okay, so this is why RAFT ensures that only the suffix can have problems. Otherwise, you will have to go all the way to the beginning and compare entry by entry to fix the log, and that might be expensive. So you don't want that case. Yes. How do you know what point you have to traverse back? So you could, for example, go to the log, followers log, and say, give me the index. If it says index number 4, you will basically go there and then make sure it matches. If not, you keep going back until you find a matching entry and then replay everything. Yeah, so you can, your most recent entry may not be a matching entry, it could be an extraneous entry, but you go back because it's indexed by entry number, right? So you go back to the prefix, most recent prefix, that's a match. That's the basic idea. So you go step by step until you find the most recent match. Is it supposed to be expensive? Well, this is going to be a linear operation, right? You are going to go backwards in time until you find a match, but that's the only thing you can do. The other thing is what was explained earlier. You can send the entire log, okay? But if this log is maybe 1 year long, because it's just a long log, you will essentially end up sending a lot more data than trying to rewind it to a point where it matches the leader. You're just trying to rewind to a point where it matches the leader and you replay the rest of the log. Okay, so it depends. I mean, if this follower was offline for a really long time, you might actually want to just replace the follower log, but it's always better to do this. In general, that's more efficient. Your question, yes.
We have a short log, the entire log instead of going back, because if a follower is far away.
Yeah. So question is there an optimization where if you have a small log, it's cheaper to send the entire log rather than sending a lot of messages saying, do you have entry 10? Then you say no. Do you have entry 9? You say no. You keep doing this until you get to 4. So that's like already you spent 6 messages asking, wouldn't it have been cheaper to just send the entire log? That may be the case. You could certainly do that. That's not what RAFT does, but it's an optimization for sure. For small logs, it may be cheaper to send that entire log and resync rather than getting tracking one entry at a time. Right. So, but yes, you're right. Any other questions here? Okay. If there are no questions, so this is log repair. I already mentioned this here. So I will briefly mention checkpointing here as another way you can do recovery. We talked about paxos. We talked about consensus. If you remember when we had done distributed snapshots, right? I talked about how do you take snapshots, how do you recover from failed nodes, and so on. So this is basically the alternatives to keeping log is you checkpoint state. Right? So logging is one approach where every operation is put in a file. When the failed node comes back up, you figure out which operations were not processed at this node. You get the log and you replay those operations. That's one approach. The other approach is you take a distributed snapshot of all of the replicas every so often. Okay? And if there's a failure, you go back to the most recent snapshot and play things from that point onward. Okay? A distributed snapshot will work if you are actually using something, or not using, the computation is something like a simulation. Okay? If you are a database where you are actively receiving requests, you can't say, I took a snapshot at midnight, I'm going to roll back there, and I'm going to throw out all the operations that were committed to the database since then, because then you lost some operations. So if you have database-like situations, logging is the right approach. If you are doing simulations, okay, checkpointing might be cheaper. You might say, I checkpoint every hour. I don't have to write every single request to a log and have the logging overhead added to my computation. Right? So checkpointing is an orthogonal approach to ensuring you can recover failed replicas to something like logging. Okay? Logging allows you to keep track of the state on a per request basis. Checkpointing periodically keeps track of the state by checkpointing the entire state using distributed snapshot. So this is something I wanted to mention as an alternative approach that's used in some computation, not in things like databases or web services where paxos and logging like RAFT like logging is the norm. But in other batch computation, this is often cheaper rather than writing logs, which can be expensive because you might see all the overhead you have to pay just to execute one request, right? All of the logging and paxos, you have to send all of those messages to execute each request. So it does get expensive. So this is an alternative that's used in certain types of applications when you are application. Okay? So I'll just say that and then we'll end it here today. Next time we will start talking about a new topic. Okay? So let's stop here. We'll continue.